走过来了，这是他命啊。他的好紧张。
Good morning.
Please make
Oh, sorry. Thank you. Sit down.
Thank you.
Firstly, I want to express my greetings and welcome. This is almost first time. This is meeting with scientists, mainly Chinese scientists, actually this kind of meeting, now over 30 years, I have sort of meeting with scientists. And then mainly you see the Western scientist, Westerner. Some American, some Europeans, and occasionally some Indian. But now this is first time meeting with scientists from Chinese community. I want to explain the very purpose of this kind of meeting. Two purposes. Number one, simply expand our knowledge, and particularly the field of scientific research. I think till later part of 20th century, I think their main sort of field, concentrate, is external thing. And when I mentioned mind, some of them reject. Just brain. Beside brain, no mind. I'm wondering, do you believe, do you have the concept mind something separate from brain or not? So scientific sort of research field, I think it is not sufficient, just external thing. The pains and pleasure, anger, compassion, this not just a mere brain, but mainly mind. So therefore, now scientific sort of the research field should include about mind. And now, later part of 20th century, now some scientists, brain specialists, now they begin to feel there is something which affects our brain.
Plasticity. Yeah. For example, like the discovery of plasticity has really changed the neuroscience.
Because of the training our mind, some people who have some sort of ability to concentrate without moving their mind, there's some change in their brain. So now begin the scientists also, some scientists showing interest, and as a matter of fact, some scientists now start some research work. Like one American scientist, a brain specialist, the subtle mind. There are some indication, some cases, brain dead, the heart beating stop, then blood circulation cease. So then, within a short period, brain dead. But the person's body still remains very fresh. Including my own teacher, after death, clinically, so they
declared
recognized as a dead person, now dead. But his body remained very fresh next 13 days. And similar cases, some 2 weeks, some 3 weeks. So now, this is something phenomena we are seeing. So now, the Buddhist tradition, we have some sort of explanation. The scientists say not yet sort of say
have the explanation. Have the explanation for this phenomenon.
So Richard Davidson, Wisconsin University, he already
initiated, no?
Sort of, they developed some kind of project to investigate such case. So that's purpose. Number one purpose is simply scientific sort of research now should expand material, external things, as well as internal, our mind.
Experience.
Then the scientific knowledge then becoming more fuller. Now, the second purpose is, in spite a lot of sort of, the development in scientific sort of research and knowledge, and with that technology, now highly developed, very useful. But many of these scientific sort of finding, result out of scientific research, like nuclear bomb and many weapons. So the knowledge, the science, unfortunately, use destructive way. That brings more fear. The nuclear sort of, weapon itself, and neutron bomb. Wonderful. But the very purpose of these things is killing. So it is quite unfortunate. So now, and then the people, the scientists who carry sort of research work, they found constant anger is, very harmful for our health. Anger actually eating our immune system. Some scientists say that. So more compassionate mind, it automatically bring more calm mind, more peaceful mind. So very important for our own health. And I think here, all the people, prefer smile face, isn't it? I think nobody prefer I think hero's face. No hesitation to kill. Oh, I think nobody prefer, you see, that kind of expression. That's human nature. Even dogs, I notice, you see, dogs, while you are giving some food, you show smile and affection. They also appreciate, isn't it? Some birds, although you may give something, without showing the human affection, they take the thing, then go. If you show human affection, dogs, you see, their tail, you see, doing like that, they really showing a sort of response to us, more closeness feeling. So now, all major religious traditions carry the message of love. With that message of forgiveness, tolerance. But frankly speaking, effect from religious tradition limited. In modern time, I notice some temples or monastery in Europe or in America, a big monastery, now almost empty. So you see people sort of showing interest about religion less and less. So now in education field, we should include, now these days I'm expressing, in our education should include, beside hygiene of physical, we should have hygiene of emotion. That we really need. Without touching religion. Not talking about heaven or some other things. Simply how to carry healthy body, healthy mind. Too much emotion here. Anger, very bad for our health. So now, the way to promote this inner value, if you, based on religious belief, the effect limited, as I mentioned earlier. Now, as I mentioned earlier, it's a scientific sort of, out of scientific research, they say anger is very bad for our health. Then some scientists say basic human nature is more compassionate. It also, you see, if we use common sense, then all 7 billion human beings come from their mother. And they survived with mother's affection, mother's milk. Then in young child, young children, I think they don't care what is difference, what is national differences, or what is religious differences, or even with believer or non-believer, not much sort of pay attention. So long, children each other play together, smiling. You see, they feel very happy. Then gradually, we grown up through our education. Then, you see, the existing education, I feel, very much materialistic oriented. So not much talking about these deeper human inner value. So now, in any case, it is quite clear. Now, in education, we should include, you see, education about how to bring inner peace. And through that way, how to create healthy body. So now, I am Buddhist. To my own practice, yes, some of Buddhist sort of practice very helpful. That I cannot share with other people. Out of 7 billion human beings, about 1 billion non-believer. And then about 6 billion believer. We already observed a lot of troublemaker among the believer. Isn't it? They say, the very thing which they believe use, you see, division and killing. Unthinkable. Whether you believe religion or not, up to individual. But once you accept religion, then you should be serious about your religious tradition. Then all major religious traditions carry the message of love, forgiveness, tolerance, self-discipline. They use different method. Some say in philosophical field there are differences. Some say there is creator, there is God. Some say no God. There is different method. I always telling, you see, we cannot say, pick up one medicine and then say this medicine is best. You cannot say. According to the patient's physical condition, illness, age, climate, then you can recommend. Your case, this medicine is best. Similarly, among the human being, there are many different mental dispositions, and due to different culture, different environment. Therefore, you see, we need different way of approach in order to promote this deeper inner value. So now, the non-believers, I feel the explanation, the importance of these inner values such as compassion, warm-heartedness. If you based on religion, then not much effect to these people. So on the basis of scientific finding, they will pay more attention. Now here, according Indian tradition, we usually describing the secular ethics without religious belief. Simply, they explain these deeper value. So,
Alex.
Alex, you once told me the very word of secular is not nice. And also some Muslim friend, they told me. So in the West, the meaning of secular means disrespect or distance from religion. But in this country, India, secular means respect all religions and also respect non-believer. I think that way of thinking, that way to understand secular means, I think, are useful. Secular ethics, they showing respect all religions and then also non-believer. So now, in order to promote about our inner value through education, only way is secular way. So I usually used to follow that way. So now, scientific sort of research or scientific finding is something very useful, as I mentioned already. People more convince science rather than religion. Okay. Like that. So that's number 2, because of the purpose.
Of our second purpose.
Second purpose. So So then, in the past, I think over 20 years, I think, it's not a scientific meeting. More than 30 times.
Mind alive, yeah.
I must introduce other people. This lady, the late Varela's wife.
Francisco Varela, yeah.
The Varela, great scientist. Also, you see, he usually say, when he explains something about pure science, then he say, now with my scientific cap. Then sometimes he refer Buddhist concept. So then he say, now I wear Buddhist cap. So great, really great. I think mainly her late husband, I think really also start this meeting.
This dialogue series. Yeah.
So in the past, over now 30 times back.
Yeah, over 30 dialogues.
Dialogue, mainly Europeans and some Indian. Occasionally some Chinese.
Westerners. Westerners.
Westerner. And then, few months ago, when I give teaching some Taiwanese Buddhist, then when I met organizer, so one Taiwanese, I'm wondering that person here or not. Correct. Oh, you? Oh, I see. Right there. Oh, he quantum physicist, and he, you see, introduced himself as a quantum physicist. Then I thought, oh, now we are going to have one meeting about quantum physics from Chinese scientists. So now, you mentioned that, so now that word, no physical, but that word brings now this opportunity. Law of causality, right?
Yeah.
Cause and effect, cause and effect, cause and effect. So now I'm really very, very happy meeting with scientists, mainly Chinese. And I welcome one Nobel, laureate. Thank you. And this morning I met, you see, his age, 82. I'm 83. So now another sort of thing I want to explain. When I met the Western scholars and discussed about, you see, these, including quantum physics or psychology or these things, sometimes I feel little
hesitant. Yeah.
Because you see, and Western sort of, scientists, their cultural background, something different. So the concept of creator. So therefore, you see, if we go detail evolution, the whole world, whole galaxies come from particle. And go that way, evolution way, is sometimes difficult. With too much emphasis on that, I feel uncomfortable. Because I respect all religion. And I really admire Judeo-Christian tradition. The millions of people get immense inspiration. Last 1,000 years, and even today. So in the future also, it will remain. So therefore, and particularly, I'm fully committed promotion of religious harmony. So therefore, out of my sort of genuine respect, you see, there are sort of philosophical view. So sometimes a little sort of concern or feel uncomfortable. Or the Westerner, mainly Judeo-Christian sort of background. So it is better to keep their own way. Now Asia, something different now. And particularly Chinese. Many Chinese are Buddhist. Wherever Chinese community there, in America or in Europe, Chinese community, bigger Chinese community, like Vietnamese community, some Buddhist temple. So, quite familiar. Then, and the Chinese Buddhist tradition, Tangsen, Kasa, Tangsen, Kasa.
Xuanzang.
So he came to India and spent some time in Nalanda. And according to some sort of historian, he met Nakabuddhi. Nakabuddhi. So when he met Nakabuddhi, of course, the direct disciple of Nagarjuna, and Nakabuddhi, when he met, very, very old. So in any way, and many Chinese Buddhists, the name of Longsu Pusa, familiar? Huh? So therefore, you see, traditionally, they're very close with Nalanda tradition, and particularly Longsu Pusa's tradition. So therefore, I'm very happy having this meeting. In the political field, over 1,000 years, sometimes we fight each other. Sometimes remain very, very close relations through sort of marriage. The seventh century, the Songtse Gampo marry Chinese princess, like that. So, in any way, the reality, we have to live side by side. Whether there is creator or not, it becomes like that. So, much better live side by side happily. So therefore, political field now since 1974, you see, we decided not seeking independence of Tibet. We very much sort of committed, remain within the People's Republic of China. So therefore, and then, you see, remain politically, remain within the People's Republic of China, provided we should have all the right which mentioned in the Constitution, including our language or these things. Then it is mutual benefit. So Tibet, materially backward, so remain within the People's Republic of China. We get plenty of money, so we can build, isn't it? Material field. At the same time, the number of Chinese Buddhists now already around 400 million Buddhist population in China, mainland China. We can help them. We can share our knowledge. Now, today's world, as far as a Nalanda tradition, knowledge about a Nalanda tradition, I found we Tibetan kept Nalin tradition. Kazoda.
Alive, Lama.
Because intact.
Intact.
Intact. So therefore, you see, we can help you to explain about Nalin tradition, like that. So now, besides political field, the environment also. Tibet, one Chinese environmentalist, he wrote one article. He mentioned to me Tibetan plateau is very important for global warming. So he described Tibetan plateau is third pole. The effect from Tibetan plateau, global warming, as much as South Pole and North Pole. So he described Tibetan plateau is third pole. So now, the Yangtze River, Mekong River, the Dichu, Mochu, Marwe, these sort of big major river, original source from Tibet. So the environment about Tibet is something we really need, I think, special pay attention for preservation of Tibetan environment. Very important. So now, finished. So
it's my turn to speak?
Yes, yes.
Well, first of all, I would like to thank you for inviting us, physicists, to come here to engage in the discussion of quantum physics and Buddhism. I really appreciate this opportunity. For myself, I'm very happy to see you again. We have seen so many times in Petra, Jordan, the mandate for the peace for the Middle East. Well, as you know, when you are talking about have to be happy, smiling all the time, with all the physicists sitting there, only two on this side are smiling. The others are really very, very serious. We don't learn to smile very much. So this is something we really...
I usually, you see, when I meet people, I smile.
Yes.
Most cases, they also respond smile.
No.
If response not smile, then I do this. Then automatically smile come. So I think you need.
Well, it is quite interesting. We are scientists. You came here. It's called scientists. And very often people would ask, Dr. Lee, what do you mean by science? In one of the international gatherings in Rio de Janeiro, when we were discussing global warming, one person raised a hand, said, what is science? And there's an interesting question there. You can spend time to explain what is science. But actually, I do believe science is a language to communicate with nature. So, like quantum mechanics, we learn how to communicate with the tiny little particle, which is the dualism, wave nature and particle natures. So science is really a language. So we learn the language, and so we're quite serious. This is just like learning Tibetan language. Science is another language.
Science is 책 걸어도 죄지 책으로. 이 죄지 책 되게 되는데 다한테 소두로.
나는 그런 거 쓰기도 나는 그런 거잖아.
책 소리도.
science lab 또 죄져져 봐.
I consider, you see, as far as I understand about science, science means, you see, investigate what's the reality. So, not content, believe, but investigate why.
Yeah, that's
How. You see, that is, to us, very familiar. The Nalanda tradition, Lungsu Pusa, in his writing, you see, he emphasizes importance of investigation and experiment, not belief. Therefore, some Buddha's own teaching, the Nagarjuna rejected, and his follower, like Jadakirti. You see, some text, Buddha's own word, they say, if you accept this Buddha's teaching, literally, it goes against the reason. Therefore, we should reject. Buddha taught that for different people with different mentality. He mentioned that, but we cannot accept that literally. So that's something unique. So in the religious field, according to Nalanda, we extensively use logic. Every point, we not easily accept, oh, Buddha taught that, must be. No. Why? So this is similar way the scientist sort of approach. Not accept easily, but investigate.
So a language becomes richer and richer. At the same time, scientists, when they try to communicate with nature, they also believe in two things. One thing is, we are part of nature. All of us are part of nature. So in communicating with nature, we certainly will look into the phenomena of life, evolution. But the other important thing is scientists always based on the evidence. So we could say evidence-based judgment, evidence-based decision. Well, there are some things could be quite complicated. You did mention about brain and mind, and when you ask me, do you believe in the separation of brain and mind, I say yes. Do you know why? Because very often after dinner, my wife and I sit together. We're married for more than half a century already.
Happy marriage.
Yes, certainly. But before I say anything, she already read my mind. And so before I say anything, she'll say, oh yes, why don't you do this? You want to go play tennis tonight, go ahead and do it. And all those are in my mind, but I didn't have to speak out. She already read all my mind. Okay? So in her brain and in my mind, there's something communicating. So I will not simply say brain and mind are just one thing. But when I said we are part of nature, so we are investigating, trying to learn to communicate with all kinds of things, biological phenomena or psychological things. Those are what scientists has been doing. And scientists always believe that what we find, the new discovery, will bring benefit to mankind. But on the other hand, you have seen that science advances in certain countries, just before the First World War, colonialism. The developed country will take charge and invade not well-developed countries, and those kind of things will cause scientists to reflect the the social responsibility of science. And most recently, because of the advancements of science, population exploded, and per capita consumption keep on growing. I mean, so the Earth is overloaded now. You're talking about scientists invent nuclear bomb, bombing the enemies. But now what we are doing is we have already changed the environment such that more energy coming in from the sun than getting out from the Earth. So entire Earth is getting warmer and warmer, and extreme weather event is starting to influence us. And suddenly we know we are in a finite system. Earth is a finite system.
Finite. No.
Yeah. So when you look at the tiny little particle, you have the wave natures, but if you have a boundary condition, and the size of the boundary is quite similar to the wavelength, then for establishing stationary wave, energy level will be quantized. So humanity, now we reach the limit of boundary condition we cannot exceed. And that is one of the things I spend most of my time working on it and worry about the future of humanity. So in a sense, it's interesting. I trained as a chemist, but when I became the president of the academy in Taiwan, we do have the Institute of Astronomy, History, Humanity, and Study Institute. Then I suddenly had to change my position from chemist to a scientist to a scholar, and supposed to be able to take care of everybody and learn things together with all of us. And today it's interesting. We are talking about quantum mechanics, and from the discovery of quantization, quantum mechanics, and humanity, and religion. We have much to learn from you. So we came here, it's open-minded. We do depend on evidence. We believe if there is evidence, if there's no evidence, we might not accept.
Humility. Quantum physics.
So
yes.
So I said, we have open mind, try to learn from you how the science, nature, humanity, and religion, all of those are connected.
Humanity.
Okay.
No.
Okay. So the purpose of our meeting I already mentioned. Then, now over 30 years, nearly 40 years, the meeting with scientists. At the beginning, some my friend sort of expressing to me, oh, be careful, science is killer of religion. Then I thought, no, science, as I mentioned earlier, investigate. The one method to investigation. What's the reality? So then immediately I felt, now I express in Tibetan.
So when this person talked about the science being a killer of religion and His Holiness should be careful, it immediately reminded him of a statement attributed to the Buddha, which says that all monks and scholars And don't accept my words simply because out of devotion and reverence, but you should accept it on the basis of having examined, just as a good goldsmith would accept a gold by first testing it out.
So, as I already mentioned, those Nalanda Buddhist master, some Buddha's own teaching, they already rejected. So I also follow that. We Buddhists, particularly Tibetan Buddhists, we very much sort of love to offer mandala.
Yeah, there's a particular ritual practice called offering the mandala, offering the universe.
Oh, so the world flat, and in the center, Mount Meru. Then the sun and the moon, same level, go
around the mountain.
Around. So here you see day and night happen. The sun, other side of
Mount Meru.
Mount Meru. Then this side become dark. So I think 1,000 years, we believe that. As a result of meeting with the scientist, the world is round. The sun and the moon, not the same level, big differences. Moon much closer, sun very far. Very far. The light years,
with so many light years.
Like that. So then size of sun and the moon, big differences. But some of Buddhist literature says more or less same size. Okay. So therefore, you see, I already rejected the flat world and Mount Meru. So I am quite sinful.
Your Holiness.
So His Holiness is sometimes a little worried because there are very devout Tibetan Buddhists, especially the elder generation, who may have done this ritual practice hundreds of thousands of times, which involve imagining the universe in this particular form and making offerings to the Buddha. So some of them might be thinking, the Dalai Lama says there is no such thing as Mount Meru, so what has happened to all this practice I've done?
Your Holiness, when we met last time in Petra, surrounded by many young students, they asked you one question, and what do you mean by happiness? And you gave a very good answer. I still remember it. Do you still remember what you answered?
Now, there was
I can't remember.
You did say that the happiness is the measure between reality and expectation.
Realistic. Right.
And then the next student asked, what is the meaning of education? And you also answer very good way. You also do not remember. Like me. I don't remember anything. Except some of the words given by a wise man. You said the purpose of education is to narrow the gap between reality and expectation.
Perception, no.
So naturally, logically, you are 1 year younger. So your memory is better than me.
Well, I do want to give you some presentation or gift.
Oh. Baby orchid.
Baby orchid.
Oh. Thank you.
Taiwan.
Thank you. Thank you. 그래서
현대입니다.
오, right, I see. Thank you. Thank you. 어?
Okay, now we shall start today's dialogue on quantum effect with His Holiness Dalai Lama. We have 4 presentations this morning, so each presenter will present for 20 minutes, and with 5 minutes for dialogue with Your Holiness, because we are short of time now. So I'm the first presenter today. I'm Shih from Academia Sinica, Taiwan, and I'm honored to share with Your Holiness my personal view of our understanding of space-time symmetry and quantum physics. To integrate quantum physics.
Symmetry가 소래.
Symmetry는 편수점 받으세요.
가.
조금이니까 편수점 받대.
To integrate quantum physics with space-time symmetry is one of the major issues of fundamental physics. Okay. Sorry, I need to bring this. Okay, sorry. Too fast. Let me start with Newton's Law of Inertia, which Newton formulated in about more than 300 years ago. The Law of Inertia essentially states a statement of symmetry. Okay. There are 2 statements. The first statement is an object that is at rest, stays at rest. Okay. An object we consider to be an isolated measured particle. The states Newton talked about here are its position in space. So let me illustrate in the next slide with the plot. So we imagine a very big flat table. Okay. You put a small ball in the middle. Then the ball will not move because every position is the same for it. If you move it a little bit, we call translation, it's the same. It doesn't feel any change. But if I tilt the ball, tilt the table only one side, then the positions are different for the ball. Some positions are higher, some positions are lower. And so the ball starts to move. Okay. So this is the relation between symmetry and interaction. A particle in motion possesses charge. Okay. Charge is the generator of change of state. Okay. When the state is the particle's or the object's position, the charge is called momentum. So if the particle has momentum, its position will change. A particle at rest has 0 charge. It has no charge. The charge of an isolated particle does not change when the position changes due to the symmetry of its state, because every position is the same for it. So when it changes position, its charge remains the same. Okay. Only when I break symmetry.
가르치고 가르치.
저는 들으셨는데 두전을 붙여셔야되나? 두전 코나 요구 마담에 내갑이야. 아니 내갑디 레스트레스. 네 두전 그 코유리야. 내갑 가듯이 교원로베나 두전 코나 내갑을 교원도 그래서. 그 내갑을 교원도 요구 태교연자 차르지 요구를 기켜줘.
Okay, so only when I break symmetry, for example, by tilting the table, there will be a force and its charge will change. Okay, Now, there is another important ingredient in classical mechanics, which is charge, which is the generator of change, and the state are dual to each other, which means if I call momentum the state, then its charge, its position, they change. Okay. So these 3 points, one is law of inertia, the other is the symmetry breaking with interaction, and the third is the duality between charge and states, are the core of classical mechanics.
Dr. Lee, your charge is not the electric charge.
No, it's the generator of change. Okay. And so, as I said, charge generates change of state. Yeah. So if state is position, the charge is momentum. If state is the object's time, the charge is energy. So if the object has positive momentum, its position will change in this direction. If it has negative momentum, its position will change in the other direction. If the object has positive energy, its time will change in this direction. If the object has negative energy, its time will change in the other direction. A massive particle with zero momentum will stand still, but it will move forward in time because it has positive energy. When we were born, we all have positive energy, so our time moves in one direction. In order for the time to move, in order for the time to stand still, a particle has to have zero energy and hence zero mass. Since change of state is a symmetry operation,
the particle energy manner particle
change of state, as I say, if you change the particle's position, we call it a translation. You can change its position or time. It's a translation. Change of state is a symmetry operation. Since charge is generator of change of state, charge is called the generator of symmetry operation. Now I come to the second statement of law of inertia. Newton's law of inertia. It said that an object that is in motion will not change its velocity. So it, compared to first, the first said that the position is the same for this particle, all position the same. The second said that all velocity the same for this particle. That's why when it has this velocity, it will not change. However, changing the velocity is different from changing position. You cannot just move the velocity to another velocity. You can rotate the velocity, change its direction. But to change its magnitude, you have to do it the right way. That's what Einstein found out. Okay. How to change, for an isolated magic particle, it does not know its magnitude. Like if we set in a train which moves smoothly, you close your eyes, you don't know if you are moving. Okay. But if you think you are stand still, but if you open your eyes and look out the window, you saw the trees moving backwards fast. Then you think, okay, maybe I'm moving with respect to the tree. Okay. So how do you generate the change of velocity? Einstein found the correct way based on work of Lorentz. Okay. So if a particle is standing still, its position does not move, but time moves. Okay. So he moves along this line. Okay. He has zero velocity. So this is the slope with respect to the time axis is the velocity. We count velocity using the unit of light speed. So here you have this this line equal to this line, the 40-degree side, and you have a square. Now, in order to change velocity, you just change the scale of these 45 degrees lines. So I can stretch this line by twice, and I compress this line by a factor of 2. Then the area remains the same. A square becomes a rectangle, but the area remains the same. But now the particle will move along this line, and it has a velocity, because when time changes, its position changes, and it has a slope. If I change the relative scale more,
탁세도 단데 두쟁기 교세저와 velocity 교세대. 교세대 교단단이야 두 교단배도네. 근데 교세대 교단하면도 교단은 코라랑 두쟁 코라랑 그 랑신기 교세저와 톨리미세 교단이요 말했어. 다디고 두 다간다 초단 두기 편준 제외 골게 시도 편준 간다 다단면라베도네.
So if you change the relative scale of these 42, 45 degree line more, its velocity will move more toward the velocity of light. So what Einstein said is that all the velocity are the same for the isolated particle, but you can never change it to the velocity of light. Only massless particle move with the velocity of light, which is the slope 1. Okay. So you have 3 generators to change the velocity. You can boost it along one direction, along the other direction, and along the third direction. So you have 3 generators to change velocity, the magnitude of velocity, and you have 3 generators of rotation to change its direction. So there are a total of 6 charges, 6 generators of changing the velocity. These are called Lorentz symmetry. Okay. They generate the change of velocity. Okay. For an isolated particle, all velocity are the same to it. Okay. So classically, as I said, breaking symmetry leads to force. If you have a test particle here and it's isolated, it has translation symmetry. You can translate in space, in time. It has rotation symmetry. All directions are the same to it because it's isolated. Okay. And it does not know its velocity, just like when we are sitting in the train, close our eyes. Okay. But when you put a source here, then you break the symmetry. The test particle, not all positions are the same because it can know his position and time with respect to...
뒤처럼 뒤너스 걸래. 샴도 쳇.
가글로.
나고 추운데 직세.
So what does the larger dots represent?
The
left is an isolated.
A more massive particle.
Massive.
Okay,
yeah.
more massive particle. Yeah. Yeah. Just another particle, and then you have a relative position. Then this particle is no longer isolated. The test particle knows its position and time relative to the bigger one.
Bigger one, yeah.
And so translation symmetry is broken, and he knows the direction because you have a direction to this another massive one. So you know the direction, and you know the velocity because if this particle is raised, you know you are moving with respect to it. But you break all this symmetry. You break symmetry, there should be force. Okay. So that's what Einstein said, velocity is relative. Okay. Once, if you are isolated, you don't know your velocity. But if there's another particle there, symmetry breaking, and you know your velocity.
근데 요구해야 돼. 평균 때문에 시에나마도 코란 찍을 밴데 두랭 짱바지. 두랭 짱바 코란이야. 요구 그 고알렉 말했어. 초게 고알렉 말했어. 베나 코란 빼고 해야 되는 거죠. 모든 릴리지나 대변한 거죠. 미좀 대변나. 인도에 넘버 샤그 말아서 미단 두가라. 안에 평균 때 이제 반항한테 신단되게 된 로테 두가 수두두고 요배 넘버 샤그를 했어.
So just like when I tilt the flat table, the ball moves. When you break the symmetry, the test particle for you are force. You are accelerate, and this is gravity. Okay, this is what Einstein called gravity. And because all particles have energy and momentum, this gravity is universal between all particles.
天数的。
Now we talk about change of states. Charge generates change of states. But how do you know there is change of states? So an observer looks at an apple and an orange. Okay. Initially, they does not move. After a small time, they both move with velocity v. And Newton said they are moving down because there is gravity. They are attracted by Earth. However, Einstein said, you do the experiment at Pisa Tower. If apple, orange, steel, freezer, they all move with the same velocity, then maybe they are not moving. It's the observer who is moving. Okay? And so in the vicinity of space and time point, you cannot distinguish if there is a gravity or if the observer is just accelerating using an acceleration frame. This is called equivalence principle. And so why astronauts feel no gravity? We look at the astronaut. Astronauts attracted by Earth and circle around the Earth. It has acceleration. Okay. But they feel no gravity. We break the translation invariance and Lorentz symmetry shall lead to gravitational force. But the interaction is such that by choosing a suitable frame at each space-time point, the astronauts feel no force at all, as if symmetry exists. Even you have interaction and break symmetry, the astronaut always chooses a frame where it feels no force, feels free, and he feels there's a symmetry. This is called local symmetry or gauge symmetry. And this special type of interaction is called gauge interaction. With this special type of interaction, you can always choose a frame at each space-time point such that you don't feel any force and you are free. And so Einstein's equivalence principle is the same as gauge symmetry. The same as saying gravity has gauge symmetry. And so by choosing a suitable frame at each position and time, the test particle feel no gravitational force, just like the astronaut. But the astronaut observed that the Earth accelerates. Okay. And so the source observer, if an observer at the source, he will naturally choose a frame where he feels no force. But he saw the test particle attracted by him, by his gravity. And the test particle will naturally choose a frame where he feels free, sees no force, and he sees the source accelerated toward him by his gravity force. And so this means if the interaction, like gravity, is gauge interaction, the acceleration is relative. The astronaut always choose a frame, he sees no acceleration. Okay. This is called general relativity. Not only velocity is relative, acceleration is also relative for gauge interaction. So over the past 60 years, we learned a lot about strong interaction, weak interaction, and electromagnetic interaction of elementary particles. They all obey equivalence principle, which means they are all in gauge interaction. Somehow, nature chooses this special type of interaction. So even when there is interaction, you can always find a frame called inertial frame where you don't feel any force and you feel free. You feel there is symmetry.
要是国中说，
ngay cái cuộc sống tôi学多了。
You want to go back?
No, I
No,
think the
okay.
对 gravity 天数才是可能是过的，人们说的长了呀，天数开发要的呗。
Alright, so essentially you're explaining how the gravity force acts.
Yeah.
So so the point you're making is that when you choose, so when the say the isolated particle,
Yeah.
isolated particle,
Yes.
when it's on its own, it has no gravitational force. Is that
Yes.
the point you're making? And the
Yes.
gravitational force only emerges when it's in relation to another particle.
No, the astronaut does not feel gravity, right?
It's rare.
Yeah, that's
Yeah.
because he can choose a special frame where he does not feel any gravity.
저 텐슈
Yeah.
라와로 될 대연도 인고 지고 매도서 차로.
차고를 나를.
예.
자성가지 텐슈도 용서를 가는 거래.
그래. 텐슈 영수도 들에 간다. 잠불이나 텐슈로 봐. 수수수 수진공업을 수수수 텐슈 레고래 나.
There's,
점리 하다 점리 장리야 텐슈 수시 중요해요 말이야.
So, given that, I mean, gravity is supposed to be universal, so are there difference in terms of forces in gravity, say, even on the world?
it's,
The north,
North
Yes.
and
South.
south.
yes, it's the same.
Same.
I mean, yes, gravity is there.
There.
Okay, there is interaction. But it's a special kind of interaction where the test particle can choose a frame that he feels no force at all, and symmetry is restored.
그래비티 코르 빠지거래 말이야.
말해, 다 뉴발 샤워로 봐. 다는 코난단 디시고래, 된디.
그래 누구 거기 숙진으로.
러렌,
시와 말봐.
말해,
자상가 숙진 그 숙진 인고로.
러렌. So the
저
gravity.
수 있으면 이집지가 않아서 수기 지지 수디지고 삼당 왔다. 차에서.
수기 개주 차고로. 수진기 개주도 차고로. 러렌.
Yes, what's the question?
So,
Okay, we are short of time.
okay.
We are short of time. Maybe we should discuss
Yeah.
afterwards.
The equivalence of space and time
Yes.
did not come through clearly. So that seems to be your main point. So if you can, the equivalence of space and time,
Yeah.
that's the symmetry of space and time that
Yes.
you're pointing out. If you can sum it up in
Yes.
a simple way, that would be helpful. Yeah.
Well, I think since we are short of time, I'll just go to the conclusion. Okay.
Yeah, okay.
So, and if we have time, we will just discuss maybe later. Okay. I don't have time to go through the quantum physics. Okay. Maybe since you are interested in quantum physics, I should spend a few minutes on the future of quantum physics. I need to integrate quantum physics with space-time symmetry. So I mentioned 4 features of quantum physics. The first one, of course, is superposition principle. It just says quantum fluctuation. So if a particle can be in state x1 and state x2, then it can be in state x1 plus x2, which is a state where the particles switch between x1 and x2.
That is
So
the
that
superpos-
an observer,
Superposition said that 니가 이be 무시하고 봐 quantum key. Yeah, the chol delay 봐 파견이 패gel해요 봐지. 그 potential 그 negable 야. 니가 이be 무시하고 봐. 단디 계지들의 the superposition said.
the particle switch between x1 and x2 is called quantum fluctuation. It fluctuates between these 2 states. And so the observer can find it sometime in state x1, sometime in state x2. The second feature is that every state has a phase. It's like an internal clock. Okay. The third is most important to me. There are 2 kinds of particles. One kind is called bosons. The other kind called fermions. Bosons, identical bosons, like to be in the same state. They like to be crowded in the same state. Identical fermions cannot be in the same state. This is called Pauli exclusion principle. So,
디아의 파티클티 느껴하는 것은 애좀체 이제 과학식이 봐.
라렐.
디 과학 관리고 관리고.
So the bosons and the fermions, in relation to like quarks, where do they fit?
but yeah.
The bosons and fermions in relation to quarks,
Oh,
and where do they
The
fit?
level.
In terms of level of subtlety.
No, it can be elementary or it can be like a nuclei.
Yeah,
They can be
애좀
bosons.
뒤집어져요.
Yeah.
Right? So it's a sort of basically it's a type of particle. It's a category.
Yes,
it's a type.
yes, 2 kinds of particles.
Risha.
One kind of
Rik-
particle likes to be
Rik-
in the same state.
참여계절이면 또 리기계절이야. The bosons.
그래서 규전 소백 안 돼서
라레.
규전 소백 안 돼서.
소백안리고.
Yeah. Okay. And a large number of identical bosons can fall into a given state. All bosons in that state have the same phase. Okay? Their internal clock synchronized. Okay? This is called a condensate. Okay? A condensate, the rigidity, you cannot just change one of them. You have to change all of them together. Okay? And identical fermions can form pairs. Once fermions form pairs, they are like bosons. They can all come into the same quantum state. Okay. So a large number of identical fermion pairs can form a condensate. Okay. And the first feature is quantum fluctuation can break.
Are we talking about natural states, or are we talking about lab states?
No, it's
This is
natural
a
state.
natural
You
state,
can
okay.
observe it, yeah. And so the first feature is quantum fluctuation can break classical symmetry. But as I said, when you break classical symmetry, there will be force. But this is not true in quantum physics. When you break symmetry in quantum physics, there is a ground state. If you are in ground state, you will not feel force. Okay. So these are the four features. And now I go to an application of so-called macroscopic quantum phenomena. Okay. Dirac postulated that for fermions that cannot be in the same state, the negative energy states are few. And he predicted the existence of antiparticle. Okay, so here you look at all the negative energy states are few. Okay. This particle has negative energy, so they should move in time direction, move back in time direction. Okay. But since they are all few, it can...
Negative energy is negative side 가지고 그래.
Then log positive
알래.
log.
Yeah. Because time is moving in this direction. For positive energy particle, you move in this direction. Negative energy particle will move back in time. But this particle cannot move back because there's already a particle. They cannot be in the same state. So they are forbidden. Okay. But if at some time I put in energy and excited the negative energy particle, make it positive, okay, then you have a hole. Then this particle can move here. Okay. So in the next time, the observer will move here, and you see a particle, and you see a hole moving. This is called antiparticle, okay, of Dirac. And so our current understanding of particle physics depends on macroscopic quantum phenomena. Current understanding of strong interaction at the scale of nucleon is based on the existence of a condensate of quark-antiquark pairs. So there are many large number of quark-antiquark pairs. They all fall into the same state. Okay. The density of these pairs set the dense scale of strong interaction. It's the nuclei scale. And we are all just bubbles. Nuclei are just bubbles in this condensate. Okay. We are just bigger bubbles. Okay. And current understanding of weak interaction is based on existence of a condensate of massless Higgs particles that carry weak charge. Okay. The density of Higgs sets the dense scale of weak interaction. Okay. So to understand the gravitational effect of these condensates and the negative energy fermion Shih is one of the main issues of quantum gravity. So now I move to conclusion.
Physics knowledge force kaji shege ba. The ngema ena the quantum mechanics machung kong de shi jabdan jorba. Tana the ku that quantum ki to ne de shi jabe na ya de shi jabdan khaga chile gors.
Sorry. I move to the conclusion. Law of inertia expresses symmetry of states. For space-time symmetry, the states of an isolated particle are its time and position, its velocity, its spin, and its metric. The metric for us to tell the length of the velocity and the angle between velocity and spin. Breaking symmetry leads to interaction. There is a class of special kind of interaction called gauge interaction, adapted by nature. It's all gauge interaction. For gauge interaction, by choosing a frame, or equivalently, you redefine what do you mean by unchanged. At a given time and position, you just redefine what is unchanged. A test particle will feel no force. You feel free and feel symmetry. even though the interaction breaks symmetry. Okay. The only non-gauge interaction known is the interaction for a particle to emit a boson into the condensate or absorb one from the condensate. Einstein's gravity theory is very successful. This is an indication he got the essential symmetries correct. The symmetries were given in the equivalence principle and his law of inertia. That metric state of an isolated particle remains unchanged. Okay. I didn't have time to go to this law, but experimental observation of the existence of the so-called dark energy and dark matter could be the first hint of the breakdown of classical Einstein gravity theory. It's likely that
dark energy said dark energy and dark matter said.
So can you explain
yes.
briefly what dark energy and dark matter is here?
Recently, there are some observation that about 4 billion years ago, 40 billion years ago,
Billion years ago.
Billion, yes.
yeah, the universe expansion accelerates.
True.
Yeah, and so that's people call they are dark energy, like pulling the
I see.
universe away. Okay, so it's energy, but it has negative pressure, so it pulls the universe away.
The energy and the two guru, tanati zamling pa kat take your wenza dark energy slag we can send this now.
Okay, so these are observations. Okay,
Observations,
and people cannot explain, call it dark energy, and they also observe that some stars in galaxy move in strange ways. Okay, so they cannot explain it and call it dark matter. So in any case, there are some observations that seems to show, they may hint on the breakdown of classical Einstein gravity theory. If there is no dark energy or dark matter, it could be Einstein's gravity is wrong. And it's likely that macroscopic quantum phenomena are relevant because only such phenomenon, a condensate, can afford a non-gauge interaction. And if you have non-gauge interaction, the equation of motion for a test particle will change. You will not obey. For gauge interaction, it's free. It just feels free. But if there's a condensate, it's no longer free. Okay. So that's the end of my talk. And our next presenter, since we are out of time, we cannot invite you to comment. We can invite you to comment after all the talks. Okay. So next presenter is Chen from Academia Sinica, and he will talk about quantum entangling and computing, quantum computing. Sorry.
Yeah, good morning, everybody. My name is Chen, and the title of my talk is an Entangled World. And I believe me that this talk will be much easier than the previous talk. Okay, so the first question we ask is what do we learn from the nature? So I show a video here that shows the small ant. Everybody already know what is ant, and you see ant already. But perhaps you never see this machine. It's called a robot vacuum cleaner. And so why I put them in parallel is because I want you to make a comparison between the ant and this robot vacuum cleaner. And this comparison is made in terms of sensor, brain, and energy. Okay, so we know ant has various sensors, of course, biological sensors, but robot vacuum cleaner, it has infrared sensor, touch sensor, and so on. And for brain, I don't know if ants have self-learning function, but certainly I know that in the cleaner, we have programmable logical circuit. And energy ant eats food, but the cleaner use battery. And in this way, we know that even nature wants to perform the same task as the robot vacuum cleaner. It uses a totally different approach. Yeah, and so the next example is I tell you this is a fantastic example that there is a small bird called bar-tailed gowit. And this bird is very small. It has a weight of only 300 grams. But it can fly from New Zealand to China and then to Alaska and breed. And after that, it fly non-stop on a non-stop 9-day trip back to New Zealand to their home. And so isn't that amazing? And so we ask the question, why, or if they are on the Pacific Ocean, how do they know which direction to go? So after a long study, people start to think that they rely on the Earth's magnetic field. And so how is that do? Is the photon, blue light, that excites a certain molecule. This molecule is called magnetoreception. And this excitation gives us a superposition state that has been explained by Professor Lee previously. And then the detail of this function will be explained by our next presenter, Professor Chen. But simply to say, this superposition state contains singulator state and triplet state. And the fraction of singulator state is sensitive to magnetic field strength. And because of that, the birds know which direction to go. Okay, so a very informative illustration of quantum mechanics is shown here using the photon. And we discuss about the photon polarization. And so suppose now we have a photon source which has is unpolarized. That means it's polarized in all directions, and then it's passes through a vertical polarizer, and then this photon will be vertically polarized. And then when it's passes through the second polarizer, which is horizontal polarizer, then no light can go out. Okay, but the funny thing is that if we insert between these two polarizers a polarizer which is 45 degrees tilted, then amazingly we find that there will be some photon coming out of the horizontal polarizer. So a human analogy is this one. So we have Batman. You have seen Batman movie number 3. Then you know that there is the virtuous good Batman has actually contains something of not so good Batman, a bad, evil Batman. So why is that? Because due to the presence of this symbiote, this is a superposition state of this good Batman and evil Batman. Okay, and so if there is no such symbiote, then what happens is then we will see nothing. Okay, so this is just the human illustration of the superposition. And so another illustration is shown here. That you look on this rotation lady, what do you think? She is rotating clockwise or counterclockwise? And some says clockwise, some says counterclockwise. And but I can tell you that if you have very good conscious, then you can decide whether she rotates clockwise or counterclockwise. So we ask the question, is the collapse of superposition state similar to conscious choice? Okay. And so the other illustration is shown here. That you see these two gentlemen, they look on the brick, and the left gentleman says that there are 4 bricks, but the right gentleman says there are 3 bricks. But we know they look on the same thing. And so the only difference is that they look from different angles. So what we learn from this, first, we know people only see what they are prepared to see. And second thing, can I continue? Okay. So the second thing that we learn is that most people do not listen with intent to understand. I don't know if you do. But actually, they listen with their intent to reply. Okay, so I come to my own field on quantum computing.
So according to this kind of way of thinking, then you can't make any distinctions between optical illusion and veridical perception. Can
Yes.
you? So how do you make such distinctions? Well, if all of this is perspectively based, then how can you distinguish? What criteria do we use to distinguish between a genuine optical illusion cases where we have illusions, or perceptions that are real? That is. So, for example, in this example of 3 bricks versus 4 bricks.
Yes.
So then there must be something objectively a fact.
Right.
So the question is, are there 3 bricks or 4 bricks, and only one of the 2 persons' perception is going to be veridical?
Yeah, right. So the question.
So because in the Tibetan monastic debating courtyard, sometimes we throw a phrase saying, well, according to you, anything goes.
Right.
But this anything goes is considered to be a bad consequence.
Yes. So you see,
because even when we're talking about quantum physics, quantum effects and so on, we're still trying to look for reality.
Yes. Yeah, you see, in our research, we rely on the measurement, the instrument. The instrument tells us if it is 3 or 4. And we don't have conscious there because the instrument has no conscious. And so finally, do we trust the instrument, or do we trust the experiment that we design? That is the real question.
The instrument ki tone any to don karanye badi dembata medemba keshe or stitch to golta kanta dem meden the instrument karipachu chema julia rale we was to chetu golkang take or now.
Okay, I continue. So now quantum computers. Okay, so we all know classical computer. The computer in front of me is a classical computer, which has a basic building block we call bit. Bit could be 0, could be 1. Okay, but in a quantum computer, what happens is that
this negative computer computer program zero binary ton yana zero yana zero yana chicks to and the pension do so diameter tone any program scores that in the quantum computer then in the classical denominator the pension bange shisha ton yana zero yana chicken core that in the quantum delia 풍선 바지 샤기 여러 군데 풍선 바지 샤기 되걸라 답 디톤에 in a quantum computer 그런 사바 레퍼 사바 단지 소도 그래서.
Okay, so in a quantum computer, we use so-called superposition state, which is not 0, not 1, but is a linear combination of 0 and 1.
네가 이거 모두 샤주고 있어. classical computer now yana 0 인 거, yana 1 인 거로 봐. 다들 the quantum computer now야 0야 임배. 네가 임배제 샤주고 그래서.
Okay, so it's like this Schrodinger's cat. Before we open a box, the cat is not dead, it's not alive, it's in a superposition of dead and alive. I don't know if you have such cats here, but once we open the box and see the cat must be either dead or alive. Okay, so how do we visualize the quantum computer? So we can use this Earth model. So you see on the top we have North Pole, and we can call it say 0, and on the bottom we have South Pole, we call it 1. Okay, but so we can consider this is the good Batman, the virtuous Batman.
Spider-Man, actually,
and on the bottom, the evil Batman is living in the South Pole. Now, what we are doing in a quantum computer, is that we actually work on the equator, where it's in a superposition state, not 0, not 1. And there are different combinations. As you can see, this symbiote is in different forms. And that is how we operate our quantum computer. Okay, so the other key component of the quantum computer is entanglement. Say, if we have two high energy particles or photons that hit each other, and that will create two particles. And let's say one is spin up, and the other one must be spin down because of the spin conservation. But actually, these two particles are not spin up, not spin down. They are in the superposition state, like this one. Or it could be not. It may not be up down. It could be left and right. So in any form, that we never know. And so now, but remember, this entanglement is robust. So even if we take these two particles apart, and so far, so that they are on the edge, the two edges of the universe, they are.
Quantum communication particle to many times and the particle katan to many times your dependent jiggy what the shukshmush nature tarabush which kakebe in a jiggy spin the yarn do and a jiggy spin the man do you but that pendant to go to get his head than direction.
Okay, so they are still in a superposition and entangled state. But the interesting thing is that if we measure one of them and find that it's spin down, then the other one will automatically be spin up. Okay, so with detection, then the superposition collapse and make the choice to be a certain one. And so again, a human analogy is that there are pair of twin brothers, but they don't know their name. He says, I'm in da da da. The other says, I'm da da da. And they don't know their name. So we try to figure out the name of one of them and find the. So they don't know their name. And so one of them says, and find out that one of them is called John. The other one will immediately knows that he's called Ben. Okay, and so that is what happens. Before the measurement, they don't know their name. And after the measurement, and we know their name simultaneously. And so I don't need to explain the Big Bang. And this is not my field anyway. So, but in a Big Bang, in a very, very short time, say 10 to minus 30 seconds, it's already small particles like a quark, electrons, neutrons, they appears. And after 3 seconds, they are already helium and hydrogen, they appear. And then that gives us light, gravity. And finally, after 100 million years, then we started to have galaxies. And then, and after billion years, then we have Earth and our human beings and all creatures. And so now if we consider that, so all human beings are originally from the Big Bang, we can say that. But remember, it's entangled, okay? So now, we have so many people, not just the two persons. Therefore, the entire society, all human beings, and we all interact with each other, and all interact with our environment, everything, all creatures, and we are all entangled. And so, come back to the quantum computer. How do we define a number? You see, everything's artificial. We say 1, 2, 3, 4, and we add a 0, we say it's a whole number. We add negative numbers, we call it an integer. And then finally, we have rational, irrational numbers, and even complex numbers. Okay, so they are all numbers, but remember, this is defined by human being. So how nature does that? Nature use a different code. It's universal. It's everything that is entangled in like our society. So, and now a comparison between quantum computer and classical computer. So say we have 3 bits, and then we know there are 8 possible arrangements from 000 to 111, as shown on the left panel. And then now we wanted to find out one of those sets. And so we go through the classical computer process. And then this will take 1 by 1. And after 8 calculations, and we get the answer. The answer is 101. Okay. And so it's like we have play cards, like 4 play cards. We want to find the heart, the red heart, Q. What we do is we open 1 by 1 and until we find the card.
computer ki nalo ya software program ke lega chebe kabla ya zero da ange chik peju chigro da zero da ange peju da zero da ange sum lembe na 00000 ni kan chik kya ya 0 chik kan ni chik kya tu se je ko mudam dam bule gures da ko zero da ange chik ti manyu kha jo ngayo na ange ngayo na tina shin ke mu manga le ngro tu kus che je da classical computer ke chik dan tu se kya yo res la.
Okay, so what happens in quantum? Okay.
So we're waiting for the quantum version of this.
Yes, we are doing that. Okay, so what happens in quantum computer is that every bit is a superposition state, and yet there are several bits. And they are in an entangled status. Okay, and so how we process it, we take a name all at once, and then figure out the answer in one shot and give the answer. Okay, and the answer is 101. And that's the powerful part of the quantum computer.
So in other words, you're saying that in quantum computer, you don't have to go through this step-by-step process.
No. Yeah.
You do it in one go, like
Yes.
a lump.
Yes.
And the answer is the same, which is the
Yes.
answer comes out in classical.
Yeah,
Then
sure.
the quantum, then the classical version ton draw na 000 yan 02 dan 06 방제 창마 지 창마 잡고 요레스. quantum ko ton draw ndo gala niga yimbe mu dina kion ndo gala debjiliya 지 잡제. And angita chipo to yores.
Okay.
But
And
I mean, this is still speculation.
no, this is real.
This is still.
Okay. Okay.
So they are machines. They are machines.
Yes.
Yeah.
So now we know, but you see, this bit is very fragile. So when we wanted to read the name, it has to be very careful. We don't want to disturb all states, including this superposition state, entangled, and all even final states. And so, but then in that case, how do we read it? So suppose now we have a qubit, a quantum bit, is shown on the top right. Now, So how we do that is, we have something called cavity, and this cavity, we bring it closer to the qubit, and so then they interact with each other, and shows new superposition status, and so this cavity plays the role of a messenger. We wanted to find out the qubit state. We need a messenger to tell us. So we are the person that wear the suit, okay? And so, in these two superposition states, we call it symmetry, anti-symmetric status. And then also we call it a dressed state for some reason. And then, so this is just notation of those status. So again, a human analogy here. So what is the law of messenger? I show using this cartoon. Suppose now we have a fisherman who cut a fish and measure the weight, and finally is 4 pounds. Okay, but then after that he cut the fish and even eat part of the fish. The next day, people ask him, "What was the fish you caught? How big is it?" And this fisherman says 5 pounds. Okay. So, and now the purpose is to find the real weight of the fish. How should we do that? The answer is we need an instrument which is called lie detector. Okay. And so, how this lie detector does is it's talk to the fisherman and talk to the user. And finally, we find out the real weight of this fish. And so that is this lie detector is called messenger. Okay. And so just a slide show what we are doing in our laboratory. So we use a microwave, and then we have a qubit, and then we have our cavity. And so we try not to disturb this qubit, yet we wanted to find out the qubit state. And so I don't want to go to details, but just tell you that finally with certain technique, we can realize the virtuous better man and evil better man, okay, and even the ratio between these two. And so finally, there's some subjects for discussion. First, if the entire universe is originated from the Big Bang, then can the whole universe still remain in the entangled state? The second question, although the humans are living in the middle world, where most of the human activity seem to classically correlated. But the nature is so mysterious, and we humans know so little, even about ourselves. So, could the quantum entanglement play a role in our daily life, and even inside our brain? So the third question is that we already learned that the basis of the present-day classical computer is very different from that of the quantum computer. So could quantum computation simulate the function in our human brain? And would this employ a quantum state control layout mechanism, saying that the messenger that can help us to think about mind-body problem? Thank you.
Okay, thank you.
Thank you.
Now I'd like to invite Your Holiness for comment. We have 5 minutes.
Chang's 제시디 년이 그게 다도 quantum physics 는 셀 조나 상 temper 다 제시 기르전에 고통지 됐어.
So His Holiness was saying that he was eagerly listening to your presentation on quantum physics, hoping that his understanding is going to get better and clearer, but he's getting more confused.
I try my best
다이네.
to make things not to be confused.
아주 낭배 떠주고 싶어 주잖아요. 진짜 좋다. 다들 제가도 카케 매들지. 봐. 다디데 마다 맞아봐만 다도 이제 작별권에 여셔. 다디 데리데 누구래.
So there is, in Buddhist philosophy, particularly in the Madhyamaka philosophy and reasoning, there is an understanding that any concept you can take as an example, and if you subject that to real critical analysis, because the presupposition, if you begin with the presupposition that the concept is discrete and self-defined, you're never going to be able to actually find anything. So any concept, no matter how robust it is, it's going to break down. So at some point, our description and our conception of reality has to be based on some shared convention and kind of, abstraction. So His Holiness feels that perhaps some of what we are seeing may be, indicating similar kind of problems.
그것도 자나라 대번이 사람 사실도 능수 타는 용단지 오쇼단지 그런 능수 좀 많이 봐 심주잖아 그 내수기 인루직 대번이 시작도
So this is why in
모티베이션을 시작이야.
classical Indian philosophical thinking, both Buddhist and non-Buddhist, a distinction is drawn when it comes to description of reality between two levels of truth. One is the conventional, level of everyday experience, where you have certain norms and criteria of validity, and then there is the deeper, ultimate level of reality. So a distinction is drawn between two levels of reality. So, it becomes very clear from listening to the quantum presentations that there is clearly a big gap between our perception of the world and the actual reality of the world. So, for example, like the cookies that we have, if we were to try to find which one is the real cookie, is it the parts, the color, the shape, the taste, and all sorts, we won't find a real cookie, but that doesn't prevent us or preclude us from the ability to actually enjoy and experience the taste.
Yeah.
So when you really probe deeper into trying to find what actually is reality the case, the ultimate truth, then you don't really find anything.
Yes.
quantum physics
No.
article 치시지.
Yes.
즉 그게 다도 제거도 한다. quantum physics. those in quantum physics talk about Tonang Shra Chen, Chitting Midi, Chowdang, Atek, and Symbolic Chuans.
So this reminds His Holiness of something that he read on quantum physics, an article written by a Chinese physicist
In mainland China.
from mainland China, who made the observation that some quantum physicists, when they, because of their deep inquiry into observing reality and trying to understand reality and the complexities that they are confronting about the lack of solidity of what you can find, it seems that some quantum physicists probably have a way of relating to the world that is less grasping, and also because of that, less emotional reactivity.
I think many years ago, after I got some sort of knowledge about quantum physics, obviously, big differences, appearances, and reality. So then I felt, those quantum physicists may have some different level of emotion. Our emotion much based on appearances. So a few occasions I express, I'm wondering, I wish someone who observe those quantum physicists, when they come across, usually we develop attachment or anger, maybe some differences. Then I think, recently, one quantum physicist in mainland China, as I mentioned earlier, actually I sort of really desire that quantum physicist in mainland China should participate here. Reason, what is the purpose of this sort of philosophical view, or not only philosophical view, deeper understanding about the reality.
Deeper inquiry into reality.
Ludruganda, the Jajala Timusum, number Tolan Johnson. And it took them to Chijilo, Debalin Juniors.
From the Buddhist point of view, one of the principal motive behind trying to understand reality and spend so much time inquiring about this is captured beautifully in Nagarjuna's writing, where he says that our emotions such as attachment, aversion, and ignorance really are functions of our conceptual construction of the world. And these conceptual, this kind of false conception of the world, and these false conceptions of the world themselves are rooted in our very natural, desires of likes and dislikes and indifference. And therefore, understanding reality is really the antidote to deal with the strong emotions.
So on the Jimmy article do some transfer.
So when His Holiness read that article written by the mainland Chinese about the quantum physicist's potential, lack of having strong emotions, he immediately made the connection.
Here is one view. One American, I think, not religious sort of minded person, I think should be scientist. His age, when I met first time, his age already 84. He helping people who too much stress because of anger. He helping over a few decades. And his conclusion is when the person develops anger, the object which that person feels angry, now mainly now here human being, appears very negative. But 90% of that negativeness is mental projection. So that's to me,
So this is exactly what Nagarjuna was, pointing out, that a lot of strong emotions are really rooted in a false projection of the mind, and this is what His Holiness is referring to Aaron Beck, the founder of cognitive therapy, behavior therapy.
Can I say something? Okay, so just to reflect on His Holiness's comment about wish and mind. And actually, when we look on the cake here, and we don't know which cake to choose, they are red, blue, and different colors. We don't know which one to choose. But the problem is not the cake, it's us. Because we have our own wish. I like the yellow ones better. Therefore, finally, I see the cake in different way. Therefore, in quantum this information, observation is so important because the observer is part of the system.
Framework,
Yes, yes.
quantum knowledge, that benefit couldn't the cake to get a peco number. That cake to get a tamakanda, Mrs. Samjudan, the Vodam, which is Tony Tamshagrava. Then I see quantum knowledge, neurochichiti, ko Yugunezu Mampuchi, Tawabol Rally, ko Yugunezu Kuran, Temper the Jumaseti, Tawabol Dinam, observative gets a shape of one out and some betination. Digi, Chicle, Goresalam.
아주 샘서 대화대 동해지신 수지 아이나.
La.
샘 소 대화 저봐. 디 동해지신 수지 아이나.
So, for example, one will have to accept certain kind of, objective facts because
mental level happiness, I think even animal accept that's happiness.
Yes.
So there's a universality to certain things.
Your Holiness, I think we need to confuse you more with the next presenter.
Okay.
So 그 dom주신을다. dom주신은 차세 먹고 뒤니 차전 저봐. 차전 뒤 때문에 남샤 샤샤 남샤 샤샤버티 그냥 그래 남샤지. 뭐 모르지. 팬이 샤샤버티 그 차세 가는 맛 되도 안 봐.
So,
근데 차전 쇼거를 다도 되냐.
So, His Holiness wants to just sort of round it up. One of the observations he would like to throw here is that. So this is from the Indian Madhyamaka philosophy point of view. That when we are examining, attributes or effects of a phenomena, the phenomena that we observe generally tends to be something that is composed of many parts. It's a whole, and the attributes and effects that we examine from the perspective of something that is whole, doesn't really hold when you reduce it. And if you look at if you use a reductionist approach, then many of the attributes and effects that you can experience and observe from the perspective of whole is not retained when you are analyzing that phenomena in a reductionist way by dissecting its constitutive, elements. Then a lot of these attributes and effects get lost.
And the positive and negative side, tartuna singi nyoa 대화도 통해서 대도 또 쉐규를 말도 다 그런 거 보고 그러니까네 아니 가서 주지 직상보다 내 말로 줘야죠.
So similarly, for example, when we make distinctions between good and bad, objectively it's very difficult to ground that differentiation. Ultimately you have to relate it to the perspective of a person or a being in relation to which something that is harmful or something that is helpful. Then you can start making kind of, distinctions of good and bad.
Okay, so our next presenter is Professor Yueh-Nan Chen from National Cheng Kung University of Taiwan, and he will talk about some entangled phenomenon in biological systems.
don't know.
Turn on the PowerPoint.
Sorry. Yep. Sorry. Good morning, Your Holiness. It's a pleasure to be here. My name is Yueh-Nan Chen from Tainan, the first city of Taiwan, roughly 400 years ago. Okay. So it's the similar things, superposition principle, quantum physics. So in classical world, no superposition, just as Dr. Chen has already explained. But in quantum physics, imagine we have a quantum particle at some point of time. It could be possibly a superposition of spin up and spin down, right? Simultaneously, superposition. And if you generate this superposition,
Superposition is the niga yimbe mutabchirela. Tana kunzu niga yimbe mutabchi. Tana spin the particle chik chat tumunil tanje and spin yandro yenda mandro ye cho ya chong yenda ma chong ye ni orwa. The ya chong yenda ma chong ye diana the actual reality to shebe na classical physics to shebe na yana particle the spin ya chong ye jida yana ma chong ye ji ni madu doso yo marwa. 야만이 뭐다. 다들 퀀텀 군주 야총년 제제 마총년 내가 숨샤도 야총년 제제 마총년 제제 네가 임백이 내가 제샤고 다들 포텐셜
어느 퀀텀 피지ክ스 시험이 있는 건게 좀 말해.
답도 간다 뭔게 배제 때 노트 되거든. 뭔가 다 풍선 지샤고 년다고 자고. So his holiness is raising the question. So according to the idea behind the superposition, would you say that it defies the bivalence logic and the law of the excluded middle?
Defies the logic of what?
The law of the excluded middle. Because in the logic, you have a bivalence logic. It's either one thing or another, or it is not.
Yeah.
So there's a bivalence of the logic, and law of the excluded middle is an important part of that principle.
Okay.
So would you say that the superposition idea in quantum physics actually rejects that, or does the violate that law?
Okay, this is very good question. Yeah.
양수들이샤. 자도 기시즈지는 권유여주. 남한도 별에 기시저리. 그 렌제 당사장 렌제 그도리야. 인베 칠스로나 인로스로. 마인베 칠스로도 맨로스로. 이제 당사로스처럼 말다.
So it sort of reminds him of a story. Once in Tibet, because part of the monastic education system is sitting for debates. Yeah. So there was an important debate, and there was one monk sitting, and then another monk was asking a question, and then he was asking, "Is it the case?" Then he would look at the face and says, "Oh, maybe." And then when he turns around and says, "But is it not the case?" Looks at the face and says, "Maybe not."
Yeah, because continue follow his idea that if you look at this spin from different angle, then this is no superposition. But you change from another angle, there is superposition. Yeah. Depends on which angle you look at the spin. Yeah.
But I mean, in actual reality, actualized reality, it follows the classical law. So this is all in potential state. Isn't it?
No. So let me continue. Okay.
Dr. Chen said you need an observation.
Observation.
Point.
Yeah.
Then it turn the final state.
Yeah.
Okay. So.
So just like a human mind, you may be angry, you may be happy, but you may be in the middle. You don't know. But somehow, like your holiness laugh to me, then I'm happy, because your action, I respond, and this measurement, your happiness bring my happiness. This is.
So according to quantum physics, you see, you cannot pinpoint happiness.
Yeah.
So it's arbitrary. I mean, any person can be happy, can be unhappy anytime. mind. Because I may have think many different
Sure.
things.
Okay, go ahead.
Just entanglement.
Okay.
그래서
Entanglement, c'est très peu de sais-je
그래.
So it's just
지금은 상당한人不的通过的就是什么了对住吧这就是对的想嘛到嘛对边让现在开始考虑
Okay, so now if you generate the principle of superposition to two particles, let's say particle 1, A and B, so at time 0, A up, B down, no superposition. But after some evolution, it could be a superposition of A up, B down, and A down, B up simultaneously. So we call this entanglement. And because when this occurs, it's impossible to separate these two particles as an individual, right? So somehow they entangle together. So you have to look at the two particles as a whole, not an individual system, right? So as Dr. Chen has already mentioned that if you generate this idea of entanglement to an extreme case, then comes this Schrödinger's cat, right? So in a black box, there's a cat, and you have a poison. And the poison can be triggered by a photon. If the poison trigger, then cat is dead, right? If no photon, poison is not triggered, then cat is alive, right? But as we know, this is superposition. The simultaneous with photon and no photon, right? Then this means cat is simultaneously alive and dead, right?
Then Schrödinger did it. Kabangbu Nielsen Shu, then Schrödinger ki shimi se de ba.
그래
Schrödinger ki shimi se ju ba. Gam jin alo le shimi chu. And then Tulan ta yo ba che. Tulan de tang da ma tang de photon ji release che ba ton yo ya che. Dan gam na ju sha be na. Da dan de kana gam kha che be na. Yana shimi shi de yana shimi suen de ba. Da gam kha ma che be rengal ya. 심이 때 시와다 수바 네가 문제 제고 여러스타 쿠즈들 버려 네가 이면 못 되야
이거 이분 모두 말봐
대네 쿠즈들 샤고라 so you would say the cat is both in the
가장 먼저
superposition state
느끼셔야 돼 내가 도가 통합문줄 중세 고줄 대신도 고줄선 세전내수 세고로 또 중세 고줄서야 돼 리벌 되는 저거 봐 다들 뭔가 시시면은是吧 现在就考试
So from a kind of in Buddhist epistemological system, we make distinctions between observed facts or evident facts and facts that cannot be observed directly but needs to be inferred. And then there may be another level of facts which require a lot more series of inferences. So all of what this suggests is that ultimately you need to be able to refer to some direct experience, observation, because otherwise the chain of inference just goes infinite.
Correct. So quantum physics, the teacher will tell you that until you open the box, the cat is simultaneously in that state. So can I talk a joke? Yeah.
Sure.
Once I explained this Schrödinger cat phenomenon to my wife, and I tried very hard, and then her answer is that, why do you want to kill a cat? Don't you know the first discipline from Buddha is not to kill, right? That's her answer. Sorry, a bad joke.
가져서 시면 돼
Then the theory the shit the magic crying kimen jabensa. The gamjunji na shimiche the tool yobachen to the kacheta macheto ne shimishi durba. The she yamus jabensa. And the chime garse doesn't. Can I shime garse say some then so much as like yours.
So I have to explain her it's a thought experiment. I'm not kidding a cat. Okay, sorry. So this superposition principle can also be applied recently to this causality, quantum causality. So now let's remind that classical causality. Imagine we have two events, A and B. We say that, for example, A event occurs before B event in time, right? Or A event occur behind B event in time, right? But somehow, what quantum physics can do now is that this A event occurs simultaneous behind and after B event, right? So we call this, there's no definite causal order in the quantum level. So this is another weird phenomenon.
The event A, the event B, Chung-Yuan A, the Chung-Yuan B Slavena, Yana Chung-Yuan A, the Yungur, Yana Chung-Yuan A, the jail Yungur, the two tone. That the quantum key on the Resident, the Chung-Yuan Gamji, the two things, some children, Chachores, A, the Mole Yung, Jole Yung.
That was it. Rabbe, you Rabbe Medapa. Time Medapa, Kiji. Any? 단 지구촌 주고 줄을 시작인 데잖아요. 끼어왔다 지구촌 열어봐. 다들 손에도 상당히 어려셔.
So I mean, in Buddhism, of course, causality is a very important concept, but you know, most of our understanding of causality is at the level of observed phenomena. So it's quite coarse level of reality. But in Buddhism, when you talk about causal processes,
단 너도 이제 슬라고죠. 지라마 올라가 있나? 겨, 내가 가와 지부신.
So within
진시시.
Buddhist philosophy, there are different schools, of course. So it's there's one school that tends to have a much, you know, for example, speaks about 4 stages in a causation. But most other Buddhist schools that are more advanced philosophically would speak about this causal process even at a very minute level, very, very subtle level, very, you know, temporarily, very, very short periods of time. So, so in that understanding, arising and cessation, disintegration are actually recognized to be simultaneous.
Okay, cool. I'm not good.
Okay, that's all.
Sorry. Yeah. So here comes the question that, okay, so maybe someone said, okay, microscopic world, I accept quantum physics, right? But for a larger size particle like us, we should experience critical physics, right, from our daily life experience. So it's a crucial question that to how large the size the superposition principle can apply. It's a very tough question. So there's one approach to address this question. Then we have to think about this macro realism, right? Before addressing this, let me remind you this Einstein, he didn't like quantum physics. And he once said that I cannot accept quantum mechanics because I like to think the moon is there, even if I am not looking at it, right?
Einstein that quantum zane kelen che mare, but the quantum the nyoro so che, and mangpuchi den ge be.
Einstein yeah the relative shigdo.
But he was a proponent of relativity theory though.
Yeah, relativity.
Yeah.
Sure. It's a great
question. Quantum ke tone she endo gal semza w to gal Einstein ke dilavres nge debalas nge mi mate be nen dawa yiga yobaji sha chi ge yes.
That is a bana sungzi mishi yebe jeno sugyoba. Sungzi mishi mebe kudula sugyo marsenda shedeat. Rada suru sungzi ni shiban yibuti zaji greshin shedeat. Di shegdwa.
So in fact, there is a school of thought in classical Buddhist tradition known as mind-only school, Chittamatra. It actually came up with a position where the existence of matter is really dependent upon the perception, and perception of matter and the perception itself were understood to be simultaneous.
Okay.
So they end up rejecting the reality of external matter.
Okay.
It's an idealist philosophy.
지금 치든 여말을 lem네. 당시 전에 치든 매번 나시 우서버 거래 전이야. 그렇죠. 당시 마저가 지 작별권에 작성 지금 작성 전에 쉐베이나 치든 샤쇼도.
So Of course, if one examines in a critical way, even matter what it is, then you get into this problem where you don't find any absolute reference. But on the other hand, you know, this other Buddhist schools reminded that mind-only school that if you apply the logic, turn it inwards, and apply it to the inner experience as well, in the end, you wouldn't find that experience an observer either. So one shouldn't make a kind of a differentiation between the reality of matter versus the experiencer. You know, it should be just same.
So, now actually, Sir Tony Leggett is also a Nobel laureate. In 1985, he and his colleagues addressed this problem by proposing inequality, and we call this Leggett-Gauk inequality. There are two main assumptions. For a large particle, then basically we can assume that realism. What I mean realism here is that because it's a huge particle, right? Before, even if I don't look at it, it is there, not in the superposition, right? That's why I call it realism. The second is a non-invasive measurement. That
measure chetan yo panong le the measure chesa jorwa kolo nebo modro to ne chetan in non-invasive.
Never correct.
The kolo yogu shukchi mo mate berche. Kolo yo shukchi mo tebe na the going to the current there. So can you explain what you mean by non-invasive?
Yeah, because in a quantum level, whenever we measure a particle, we always disturb it. But for a large particle like us, in principle, we should be able to measure a large particle, without disturbing it, right? This is according to our daily life experience, right? So under these two assumptions, Sir Leggett, he proposed an inequality. Say, if an experiment observation violates this inequality, then that means there's a classical physics breakdown. Quantum mechanics is correct. So of course, the experiment is very difficult. But in the past decade, experimentalists had tried to, some preliminary result. So they perform an experiment in a micro-sized device. Although micro-sized meter is still very small, but compared to the size of electron, it's already very large, right? So they're using this device to test this inequality. You see, there's a 1 point, it's a green arrow, larger than 1, right? This is violation, right?
Can you explain that? So what's the point?
Because the violation, I mean, says that if you have you measure a value violate greater than 1, then it's a violation of this equation, inequality. Then that means the two assumptions I previously said is broken. It's not true. So it somehow means that even for a bit larger size particle, it seems quantum mechanics applies, right?
그게 정로 당시 요소도 가셔 과면도 저도 정수도 그 과면도
그 그런데 내가 대원 들으셨다. 나 퀀텀 기 남주 되는데 이제 내주망 보지 용달이야. 그 참여 내가 간마도 매버체. 니리 그 녀원의 대보여베 라벤 내가블이야 퀀텀 기 남주디게 tunjume wache munzi chigi orbas tatanda chine chisu takche saba chebe dumdelia rapen ko nyongo ngara jo nyong tuege rimba di kanle quantum ga namju tungu yobachi ta tutu yoresa. So am I right in understanding that the point you are trying to make is that a lot of people assume that many of the quantum effects are felt only at the subatomic level.
Yes.
But now experiments are beginning to show that in fact, these effects could be observed at a more macro level.
Yeah. But I have to say that, to be honest, there are some physicists don't believe this experiment. There are some debate, right? But debates in science is a good thing, right? It makes science progress.
The quantum namju the 참여 내가 깔마도 라베 내가 샤투 요다면 단도 접어 요래서 되는 단도 그 experiment 돈에 라베 내가 샤투에
그 차와서는 좀시 들어가.
라
좀시.
좀시 뒤도 뒤에 참여 간 쓰고래 subatomic level 간
그 저거 요구를. 라베 내가 뒤에.
네.
그 참여 내가는 요시면 있는 라베 가는 요거 쪽으로.
라레
참여 내가는 요거 마시는 라베 내가는 요거 쪽으로.
또 이나 그런 남주디 그 라베 내가 튼튼만 뜻있게
그래서 뒤도 좋아요는 벌써 또 라베 되는 거야.
Okay, so so next is main topic, quantum biology. So you can ask the question: can this quantum mechanics play a role in biological system? So one of the recent hot research topics is that for some photosynthetic molecule, it does show some quantum coherence. That means as superposition principle in this photosynthetic molecule. And that is when this kind of molecule, you see there's an elliptical shape, there's an antenna. Its function is to absorb a photon from sunlight. So after it absorbs a photon, the purpose is to transfer the excitation from the elliptical shape to the reaction center, right? Then between this elliptical shape and the reaction center, there's a molecule we call FMO molecule. If you enlarge this molecule, you see these 7-side things. So before, people believe that the transfer of this excitation is a classical way. They say 1, 2, 7, 3, then to reaction center, or 1, 6, 5, 4, 3, then to reaction center, right? Classical, definite pace. But there's evidence shows that this excitation, when passing through this protein, goes all possible ways, right? Superposition, simultaneous to pass, okay? All possible paths. Again, some scientists doesn't believe this experiment. There's debate, right?
Yueh photosynthesis, yueh energy sogo dugala. That Sudan the tenga classical ton de shijagures. The inetan Kashik Chebacheti, Rotan de Peche quantum key, Namjukuton de Shijagutus, Laburin, and the Chebachen residu.
So there's other observation in different molecules. So the second example is that Dr. Chen has already mentioned that some bird can sensitive the magnetic field. And there's a theory that in the bird's eye, maybe there's some kind of molecule. For example, there's a two spin. When the birds fly in the daytime, absorb a photon, then this creates some kind of entangled state. So this entangled state coupled with the magnetic field of the Earth. So this some complex way they can sense the magnetic field. Of course, this is a conjecture, it's just a theory. Now, there's no experimental evidence for the moment for this bird navigation things. Okay, so here comes.
Earth gravitation ya nyong tunye jida ane de tone quantum ke superposition ke niga yimbe mutne yoro tu zutide de sheke gore stay ne tan zu shire sekdu now.
Okay, so since time's up, so here comes the end. So maybe some discussion that maybe after billions of years of evolution, the natural species has already found ways to make use of quantum mechanics, right? The second thing is that it's a fundamental question. Maybe somewhere in our body, we're already making use of the quantum effect. We just don't know, right? And the third thing is that maybe it's a question, and we have this indefinite causal order. So how this will influence our concept in the normal causality? That's the three questions. So I think I should end here. Okay, so thank you.
Okay. So Our fourth presenter is Dr. Lin Zhang-Yu. Yeah, thank you.
So it's my turn. My name is Shawn Lin. I'm from New York. I'd like to move back quantum mechanics by 100 years to the beginning of quantum mechanics. I'd like to talk about how to use quantum mechanics to describe sunlight and what's the consequence of the descriptions to our daily life. So I'll talk about modern photonic revolution, the sun, the light bulb, and the modern photonic chips. I was born and raised in Taiwan, but I left Taiwan 35 years ago. It's the East Coast called Hualien. We have beautiful beaches. We also have wonderful mountains, just like here, so it's very natural. I'd like to talk about the sunlight and the light bulb and photonic chips. So sun is the first light. It's the engine for life on Earth. But also the sunlight contains multiple colors.
So it's also saying that the word first again has to be relative. So in relation to our universe system, galaxy, we're talking about this is the sun, first sun, the sunlight.
There's limitless stars.
So there could be
These are
suns.
That's true. Okay, sun is one of the first.
So difficult to say.
One of the first.
First light.
All right. So it's one of the first, one of the many.
Okay, one of the first, okay. I think you should use the word our sun.
Okay,
Our
that's
sun,
true.
yes.
Our sun. Okay, that's true. Self-centered.
Oh.
Yeah. Okay. Okay. It's a young sun.
Right, that's right. Right.
Okay. The sunlight contains multiple colors, from the red, the yellow, the green, and the blue. Different color has different brightness intensity. And that brightness has a distribution function, which I describe in the very bottom here. Some are stronger, some are weaker.
Correct.
The intensity distribution that I show in the bottom here is non-trivial. It turns out this distribution cannot be explained classically, cannot be explained by the postulates of a light as a wave. It has to be explained by light particles. Light has to be a particle. Okay. Planck used this postulate, this existence of photons, and also assume light emission and light absorption has to have a detailed balance called equilibrium.
classical tone the quantum
With these two assumptions, light as a particles and the detailed balancing, Planck was able to describe beautifully this distribution curve. The success of Planck signified the beginning of quantum mechanics. Namely, even light as a wave has to be explained as light as a particle, has a fixed energy and fixed momentum. So that's the beginning of quantum mechanics.
German Max Planck said, no?
Ah.
German physicist, Max Planck said, quantum.
So this is the story I'd like to share. I'd like to first introduce Thomas Edison and Max Planck. Technologically, Edison invented the little sun on Earth that we call light bulb, that generate illumination for the welfare of human beings for past century. That's the technology. Scientifically, Max Planck postulated the quantum of light called photons. That sets the foundation. He's one of the pioneers. That sets the foundation for quantum mechanics. We then use quantum mechanics to describe quantized energy level in atoms, quantized energy bands in semiconductors. We then study the transition between the quantized energy level that give rise to the second light on Earth. Okay. For example, the lasers and LEDs.
Laser da duzre. The laser da duzre gorwa. That quantum katone.
Okay. So I'll talk a little bit about lasers and LED and its consequence for our daily life. Recently, combining modern photonics and nanotechnology, we should be able to, and we will be able to generate endless renewable energy to power the LEDs, to power the world, to generate clean water.
LEDs la to thing some log share message log share to message so to the ma ta mandawa ku log yuru bote to ya dan LED tere na
세상에 티가 줬어.
that get the quantum to the ship gores that into did on the kind of photonics la to work to ne tuje to ne so dante the nanotechnologies to time to rembe energy mangu so tours no.
So I start by talking about the first sun, our first sun on Earth. I have to be very careful. So solar radiation, our first light on Earth. Specifically, I'd like to talk about next generation solar panel that is going to be super thin, super efficient, and very flexible. The sun is free, but the solar panel is expensive. Solar energy is wasted when it strikes a solar panel because of a reflection. Large percentage has been reflected. So our first job is to eliminate optical reflection. How do we do it? If we can do it, then we can increase the efficiency and lower the cost. We can learn a lesson from the nature. When sun strikes the earth, it goes through many layers of air. The air density has a gradual change from very dilute in the outer layer to very dense in the inner layer. The gradual change of air density allows the full collection of sunlight from all angles and for all wavelengths.
The ozone layers are the quads gore.
So where would the ozone layer be in this graphic?
Okay. In this graph, there are all kinds of different layers. Outer space is outer space. Inside here, Earth is roughly here. Somewhere in the middle is right here, 1,600 foot, 1,600 meter. So these are different layers of air.
Yeah. So where would the ozone be? Ozone layer?
Where would the ozone be? Probably asked Dr. Lee.
The second one, 40 kilometers.
Okay.
Roughly here.
40 kilometers.
40 kilometers, the second layer.
Stratosphere.
Right here. Here. That's where ozone is. Thank you. Ozone contributes.
I think sometime back, I think maybe 2-3 years ago, you see, because of the industrial also the
Industrialization now.
I mean, people who connected with factories, you see, they pay more attention about the ecology. So as a result, the damaging ozone layer much less.
So His Holiness was, exposed to a presentation by someone who actually had some statistics to show that, because of the environmental regulations, there has been a slowing down on the ozone layers damage.
So do not use the freon, use the replacement with hydrogen.
Chemical
So this nature's gradual change in air density is very effective in fully accepting light. But it takes 400 kilometers to do it. Now,
the kilometer shift gets ma yong go tu gala the lungi density level ko to ne nime we de kanda sal le yon du gala ya cha chu bu shu ju to ne yong tu yores that the lungi ma gyuba de chen the current is there sha. Yes. So can you explain, because the idea that the sunlight, because it is coming through this long process of layers of air, it becomes more efficient. So is it similar to sort of pointing like a magnifying glass to concentrate the sun power? Is it something like that?
The principles of fully absorbing light, right? If you try to minimize reflection, you do not try to put something hard to it. It's almost like a sponge for light. Soft landing. How do you achieve soft landing of light on Earth? You make a sponge, make it from very dilute to a little bit denser, the gradual change soften the refraction in a gradual way. So it's almost like a very nice and very slow.
Reflection. That the mayo the case the solar panel to get the manche, say ma power pa lord waters because of the panel the tata church.
Good?
Yeah.
Okay. Similarly, we can create a gradual change when solar energy comes into a solar cell. We can create a gradual change in mass density. So we start from very dilute layer to heavier layer. So they have a similarly gradual change. But this gradual change in this case happens only a micron. So we reduce the gradual change from such a long distance to a very thin layer on top of a silicon solar cell. The effect is dramatic. If without this gradual change coating, the refractivity is 30%. With this gradual change, the refractivity is only 2%. Most light can get into the structure. Once light can get into the structure, we now need to maximize absorption. We also need to minimize the use of material. It turns out those are interrelated. I'll explain, and I'll probably have another 5 minutes to go.
그 로스에 더 인지식 소리로 하듯이 무슨 벽에나 전에 쉐변 그래도 또 그게 스미야 소리.
그것도 외심 두고요 말이야. 어떤 쿠란들을 셔다 지도 두고 외심 두고 주고 그래서. 근데 님의 이름만 잡은 데가 살이 없음 게 그래서.
Okay. So we now talk about a new challenge of maximize solar absorptions and also minimize the use of solar material. If we assume Worldwide electricity usage is 32 terawatts installed using solar cell. If we also assume state-of-the-art efficiency, which is 200 watts per meter square solar panel, you can do the math and you find the total solar panel you need is 0.15 million kilometers square, a huge area. How big is the area? It's about a fraction of Sahara Desert or a fraction of Mojave Desert. It's a huge area. If you assume a finite thickness of a solar panel of 250 micron thick, you know the volume, then you know the density, you know the weight. The total weight you would need is 100 million tons of silicon crystal. We know the global silicon production is 1/3 of a million tons. You can do a very simple math, you find you need 300 years to do it, which is too long. So the next solutions, we do need to have a new solution. The solution is to go for very thin solar cell. You reduce the thickness to very thin. But once it's very thin, it's not absorbing anymore. So it seems to be a contradictory requirement. You need to have it very thin, and yet you need to have it very efficient. So the next challenge in the next generation solar panel is going to be super thin and super absorbing, but seems to be a contradictory requirements. How do we do it? We need to invent and come up with a new optical principle. What are the new principles? We go back 300 years from now. Before Newton's time, we keep on coming back to Newton. It was believed light was colorless, the white light was colorless, and that the prism itself produced the color. The prism.
Prism solar.
Prisms and to her youngsati. And the shade of your the shade shine to go word shade of the shade and so judgment tungorba. The Gema Samjulia, we Koran Kato Mavase, and Kato Tigeti, we posa the shake on a server, such as something about Islam.
But it turns out the prism does not produce the color. Prism simply bend the color differently for different colors of light. For example, it bends the red light a little bit less, bends the yellow light a little bit more, and bends the blue and purple much more. The extreme light bending would be in the following sense. You can take the light by bending from not to the third quadrant, but into the fourth quadrant, and actually parallel to the interface. That's the most extreme light bending one can achieve. If one can achieve this kind of light bending, light will be traveled parallel to the interface inside the material for an indefinite length, without limited by the thickness of the thin film. So that would be a dream for solar absorption.
Tana kusukangan tewa te inima nimewe tukurwa nimewe dutugalia dusa tanda peju jeti cheyon dugala be lomang bu koyare shas tati induko gywa tangje dusa di trap chapter 7 tati ani chapter 7 dugal tayam shukchim dutuya tapshe kar yor islam dugala ani kugdang keba tolya tagje cheje and jisam ku kutunye delia ani
Okay. Here I show a cartoon and schematic of what things can happen by using nanotechnology. Sunlight will come into this type of three-dimensional nanostructure. It's going to be bended with an angle. So it's a deterministic bending of light. It's not random scattering, but light will be all bended along one angle. If the angle is 90 degrees, it's going to be parallel to the interface. If it's parallel to the interface, then you have effectively infinite path lengths within a thin film. So light can travel parallel to the interface with a very thin layer. So you can solve two problems at one time. Can that be done? The answer is yes. This has been done the past year. This is a three-dimensional image of such kind of structure. The optical design has been done. The nanofabrication has also been done. To the right, I show you an individual nanostructure. The geometrical shape acts like optical funnel to receive light fully. The arrangements of the funnel into a square array shows a square symmetry. The symmetry dictates the flow of light such that when it comes in of angle, it's always been bended parallelly inside the structure within a very thin film of 10 micron. So that can be done, has been done demonstrated recently. I'm going to show you a simulation results as well to show such an extreme optical effects. This is a computer simulation from a good friend of mine called Sajid Jong. The right-hand side showing light coming into an optical funnel, but ray arrow, a little bit small, show light is going to propagate parallelly into the interface. So there's a propagation parallel to the interface. The left-hand side, I showed intense fields inside the structure, but only within 10 micron. Light have been concentrated, funneled through like a vortex of electric field within a 10 micron range. What's the consequence of it? We're able now to achieve 98% of every solar absorption within a very thin thickness of 10 micron. Okay. Seems to be impossible task, but now can be done through nanotechnology and through this new invention. Why is it a big deal? Because state of art show us we need to use a thickness of 200 micron thick before. But next generation solar cell is going to be 10 micron thick. What does that mean? The total weight that we need of silicon is going to be reduced from 100 million tons to about 5 million tons. What does that mean? That means the global silicon production is 1/3 of a million. That means in 15 years, if we make it into practice, we should be able to provide all the energy purely from solar panel. So we're able to, in principle, have a blueprint now to have all the energy coming in from solar power, all the 32 terawatts. So finally, we have a plan for a sustainable future. Through the first light on Earth and through the novel optical design. I don't know how much time I have.
Your time is out.
My time is up. My time is up. Let me go all the way. My time is up, so let me go all the way to the very last one. Just a summary.
So
Let me just say,
just out of curiosity, how thick is that material?
the thick material
Yeah.
can be as thin as 10 micron, so it can
10
be very
microns.
flexible.
10 micron is how thick?
10 micron, your hair is about 100 micron.
Micron.
So 1/10 of a hair.
툴수지.
되게 독력의 전부 야저 두두스람 그 시위답도 차고를 나래.
So it can be very thin.
Very thin.
Yeah. Let me summarize this because I'm out of time. The impact I'm happy to share with you of optics and photonics as a result of quantum mechanics have many impacts to every corner of our daily life. Biomedical applications such as laser knife, such as skin treatment is very useful now. Energy application is very huge. Hydrogen production, water desalinations, solar cell. For environment is also very powerful. All the pollution detections, cloud thickness determinations. Information science is clearly all the displays is the consequence of optics and modern photonics. Automation, the drilling, machine vision, laser cutting, very powerful CO2 laser now being used to benefit mankind, very quick, very nice cutting. Also basic science, the laser spectroscopy, the laser tweezers, the nonlinear interaction, and so on. So the quantum mechanics, light, and optics has been a very instrumental aspects of it. Thank you very much.
Wonderful.
So now I invite Your Holiness to make the concluding remarks. If you feel hungry, we can go have lunch.
No, nothing. Oh, really? Wonderful. Those also the Dr. Shih did.
Yeah, the researchers, they've really thought deeply.
Wonderful, wonderful. As I mentioned at the beginning, now more research work on how to reduce anger. That's important. Truly. In today's world, I think rule of anger is much stronger than rule of compassion. That must change. Quantum physics 가르쳐야지. 나도 수습해 공주의 샤워하다 두고 쉬는 것도.
Yeah. So while we are all, inquiring about quantum physics, but in the day-to-day life, what gives us a lot of problem is really about the strong emotions causing a lot of difficulties.
At a global level, I think really, really very sad. This very moment, we enjoy peaceful. But meantime, hundreds of people killing and facing starvation, particularly those children in Yemen. They done nothing. The soldier with weapon, there's maybe some reason to eliminate them. But those children are dying. So that's today's world. And the religion itself now making more division and killing. Really very sad. So I hope more and more scientists, as I mentioned before, after sort of research work, then finally, we human beings, all these sort of knowledge in human mind, not animal mind. Now this knowledge, I think we should have one aim, goal, not just to develop a new idea and some article, then get some name. Right? So that's started to change.
So the motive behind scientific inquiry should not be just confined to, just innovation, finding new things or getting your name and so on, but we need to have always maintain the bigger picture. What is the goal of scientific inquiry?
Okay.
So if world is too much violence,
Yes.
and then finally the scientists also suffer. We are part of the humanity, isn't it? So I think we should think the well-being of humanity. And the religious people also, think that, not just my religion, not like that. Think how to build the happy humanity, peaceful world. So scientists, as I mentioned this morning, I think really quite influential in the society. So you also should think about how to achieve happy world and how to reduce this the suffering of human creation. They are quite sufficient due to global warming. a lot of problems. Now, it is senseless beside the natural sort of problem, disaster. We also, you see,
Add
more problem. Very sad.
Now I invite Professor ITD to say a few words.
Well, I agree with what you said. Holiness just said about humanity, what we should do. I just want to mention that when we said Max Planck invented quantization, actually at that time, scientists tried to understand the break body radiation, like something's oven, in the oven, when the firewood was burning, we do see some radiation, some distribution. At that time, classical mechanics could not explain why the wavelength distribution should have a peak and go down. And so one newspaper was having a competition, said, how can you explain the break body radiation? Max Planck didn't really know quantization. He only knew that in explaining the break body radiation, he has to put energy in proportional to the frequency. So energy will have to exchange in a unit of certain quanta. So actually, the curiosity try to understand the break body radiation necessitated him to put the energy in a quantum form. So that was the start of the quantum mechanics.
Quantum tampunyati, the mepa into the make it work, the namjul gate, cook to it, the deshe, classical gaton, Japtu Yomaris, Mavin San, Sawachi gaton, and Tendruche, that the deshe Japtu Suyan, never taking slapche, the Chevron Max Planck, the Shejaba Kablaya, Kandachi energy, the frequency in Barun, Dewi was to a shame in Dugala, and the quantas head, Hurrying to go tum tum, neighbors, according to.
So very often, teachers want to teach children to be creative, innovative. Creation, innovation is really not coming from nowhere. Most often it's a curiosity in trying to understand certain things and pursue the answer. Then you find something new.
The negative, curiosity. No, that's true.
The curve is the reality.
Yeah.
No one can do it.
That's true.
Non-classically.
Yeah.
Someone has to postulate something. Planck was so clever, so creative.
Yeah.
He said energy must be quantized into discrete levels.
I don't think the Max Planck was so creative, so smart. It just turned out that if he want to fit the curve, he just put the energy in the quanta. He didn't know why. He didn't really know why.
Okay.
Max Planck the energy dinal devoyo bachi hako bakanshi sila kharchin devoyo bati kimsang hako yo marasa jail mato.
Max Planck wrote a book on black body radiation. I read it. On almost every chapter, he reiterates, I have to quantize the photon.
Okay, so I think time is up and this session is closed. We have a break for lunch. Thank you.